Oh, well, okay. Yeah, I have more students now. Okay. So I suppose you see very well the whiteboard, no? Okay. Now, we study now the guy. I like you activate the microphone and answer me because when I open the whiteboard, I don't see the chat. I see the chat in the laptop. However, I need to update my password. So now it's disconnecting in the laptop. Okay. So now I try to explain that so far we study no in one point the vector field. No, we study in the one specific region or bunch of points in the vector field. Okay, this is a global property. But to understand global property, I need to start explaining line integral. See, well, professor, but how many integral we studied in calculus 3? I promise you this is not the last one. It's a new, but that's not the last one. We have another one more. But to understand definition line integral. Line integral definition is, look, let me explain the geometry meaning, and after that, we want to discussing. For example, we have one point here, P1, we have another point here, P2, we have a curve connecting both points. This is the curve. C is a curve. I want to compute the line integral. The name of the line integral is no good name because actually in the majority of cases it's no line, it's a curve. But historically, they call the mathematician who created this idea called line integral. And everyone in the world know by this name, line integral. Entonces no necesariamente es line, es a curve in general. Entonces you have the symbol integral again. Your specification here, C, que es the curve. Similar to the thing we are doing double integral. Remember, double integral, you specify the region, no? Region. After you put the limit, but not limited now. So we have the integral function. Suppose the problem in 2 dimensions. Of course, we study in 2 and 3 dimensions, but so far 2 dimensions. And this is ds. Pero what the hell is ds? ds is the look. We are doing a partition here, but the partition is along the curve. And any partition you consider infinitesimal r length, ds. The ds is infinitesimal r length. It's very, very similar to the thing we're doing in Cal 1, but in Cal 1, we are doing the partition or in the x-axis or in the y-axis, depending the most convenient way, no? However, no. In this case, we are doing the partition along the curve. Of course, the curve is a specification, no? You see in the example. Okay, so now, wow, it's weird. No, weird. It's the same idea that we study all the time. Because when you define integral, always the integral is the Riemann sum. You know that, Riemann sum. And the Riemann sum is, well, is the sum, summation. Summation what? Summation the multiplication. Summation the multiplication, the function, okay, by the way, this function is a scalar. Everything is a scalar. Nobody say nothing is vectorial here. And so far it's a scalar. So the function evaluate in the specific point. So inside the one specific interval, you select either way. And the symbolic way to indicate this is after. You know, you are familiar with this. a multiplication by the delta S. Okay, this is the difference between this is infinitesimal and this is not infinitesimal. This is finite. And you add in this summation every pieces. Let me put here pieces of this partition. 1, 2, 3, 4, 5, 6, 7. No, and you apply the limit when the delta S approaches to 0, que es equivalent to when the delta S and ds is the same. Entonces, it's the same. It's the same. Basically, you have a curve, you are doing the partition, you plugging in inside this value of the partition x and y, and the function, hypothetical function. I don't know what is the function f. And your multiplication, you adding, Riemann sum, and doing now the infinitesimal to small, and you get the line there. Okay, entonces now, bueno, okay, I understand, professor. But what is the application? What is the meaning? What is the way can you use it to compute that? Okay, let's discuss in the meaning. The meaning is, suppose, remember, I repeat the same idea several times. Suppose que the function f. So when somebody asks you, what is the interpretation of one integral? The first question that you need to ask by the other people is, well, depending on the nature of the integral function. Suppose que the integral function in this case is density. But I want to take advantage of density because in triple integral we apply density. Look, in triple integral you say that this is density function. Density function. And by the way, this density function, well, no, it's not constant, it's variable because I suppose hypothetically solid, okay, the density is different at any point. But the unit of this is kilogram divided by cubic meter, no? Because it's, well, this is international system. It's a British customer system, it's a pound per feet cubic, no? But it's not important. The important is a mass divided by volume, no? Mass divided by volume. Suppose in this example, okay, this is the wire in which the curve represents a wire, no? In my mind. And then this wire have a mass. It's obvious, no? But you know, this curve is represent the wire. You can suppose one estimation, good, super good estimation, is one object have one dimension, because the only dimension that's important to compute or to take care is the length. You know, it's a length. And so it's one dimension object, of course, living in two-dimensional environment, que is xy. Similar idea si es three-dimensional and xyz. But in this case, I suppose que that function is density function, pero no volumetric. Density function, no? This is mass divided by volume. No, es linear. Linear density function. So what is the interpretation of this? Bueno, es kilogram again, is a mass, but divided by meter linear. O sea, it's supposed a cable, a wire, que have 3 kilograms per meter. It's another way to see that, right? Okay, entonces now, in this case, no call rho. This Greek letter rho. Called mu. This terminology is the physical. When there is a linear density is rho. When there is mu, sorry, mu. When there's and we have another possibility, no? There is suppose two-dimensional object, no? Suppose, pero no here. In line integral is one-dimensional object, no? It's a curvy, but I promise que in other lecture, not today, we study another integral. It's the last one, I promise. And by the way, guys, I want the decay. No, the last class, you know, before the last class, I want to dedicate everything to integrate everything that we are learning so far about integral, because they are confusing things. What is the meaning? What is the substitution or parametrization? It's confusing, no? Because I want to integrate every idea to understand that everything is similar, it's the same thing. Okay, the other is no linear, sino es surface density function, que the letter que we use is sigma, x, y, z, and this is also kilogram, pero for meter cube. This is applied in the one surface, for example. Suppose the surface, suppose que the surface is the one material, and this material, of course, have a mass, pero no. Today we are talking about line integral, que is reference to the one object and one dimension, not two dimensions. And before, yo esto de triple integral, we suppose que es de solid, pero today is not solid. Entonces, si you suppose que this function is a linear mass density, and the S represent the infinitesimal arm length, when you are doing the integration, remember the integration is a sum, it's a Riemann sum. You have kilogram, so the dimension is kilogram per meter, multiplication by this distance is meter, no? Cancel out the meter. Entonces one interpretation for the line integral is a mass. The mass of what? Of the wire, of the cable, okay? Que no necesariamente es a straight line, no, it's a curvy bar, and you compute the mass. It's under the supposition that we are talking about linear density function, no? F of x is linear density function. However, what happened if you suppose that the function f of x, y is equal to 1? It's 1, the same unit, kilogram per meter, but it's 1. You see surprise that when the one function is 1, magically happen the dimension of our problem is reduced, no? Do you understand? And the triple integral, when the integral function is 1, it's the volume, and the double integral, when the integral function is 1, is the area. Actually, it's no area, entonces it's volume or it's mass. Okay, in this case, what happens if you have integral function 1? So basically, my problem is reduced like that. This is 1, yes. So what is the interpretation of this? What is the answer of this? Opinion. I know that you never understand very well this part. I don't know why. But little by little, you need to improve in this direction. Nobody have answer. Activate the microphone. Okay, question 1. Do you understand a little bit the meaning of the line integral? And second part, what happens if the integral function is 1? Guys, what happened? You are sleeping on. Come on, opinion. Yes. What mean yes? Ellie, yes. Come on, guy, answer me. I don't understand anything. Please, you say, Professor, repeat again or something.
So if the integral is 1,
Uh-huh. Entonces, when you multiply 1 times ds and you are doing the Riemann sum, what's the answer? Can we expect?
C, since we're integrating them.
C es the name, la que María, ¿no? Pero how old is María? O sea, ya es any quantity.
So S.
S. ¿Y what is S, in your opinion? Capital S, ¿no?
Yes, capital.
Ajá. What is capital S? It's the R length. Makes sense or no?
Oh.
O sea, si you suppose que the density is 1, the thing que we are doing is the computation, the R length. Exactly the same we are doing in Cal 1, in Cal 2. Do you remember in Cal 2? The formula for the R length? I suppose you remember, right? All right. Yes or no? Guy, I am talking alone. I need more participation.
I don't remember. No.
You don't remember the R length formula in Cal 2?
Not
Is this integral from a to b of the square root of...
No. The answer is yes or no. I don't want you repeat the formula. The formula is irrelevant. I want to write the formula right now. Do you remember or you don't remember?
No, I don't remember.
Okay, no problema. No problema. Okay. Look, the next is how we compute the line integral. To compute that. How you compute that. Okay, it's easy. Because the only thing you should do is parametrization. So you take the curve C, I put it now in red color, and you perform the parametrization. And when I have 2 dimensions, entonces x equal one function, I want to call x of t. T is the parameter, y is equal y of t. And you declare one specific domain que is a subset of the all real number of both n between a and b. This is the parametrization of the curve C. You know several examples. Today we practice more. Entonces now, using this idea, wow, fantastic. You convert this problem que es along the curve C, que es curved, and one problem in one dimension. This is the t-axis, and between A and B. Okay, this is my new interval. And this allows us convert this line integral like a one integral exactly we are doing in Cal 1, because you integration with respect to t and t vary from a to b. So basically I convert this integral in another integral dt a to b. Do you understand this? Okay, pero no. I need to explain in detail everything. I bring a lot of examples. Okay. Now, you understand parameterization. But parameterization, I explained one day que es possible express it like a vector value function. So R of t. R of t is a vector, and this is 2-dimensional vector, no? The first component is x of t, so that function, comma, y of t. And when you are doing substitution, we actually, the thing we are doing is substitution. So when you parametrize something, you change the variable. So the traditional xy variable to the new variable get t. And this open the door to make easy any integral. So now when you finish the The parameterization, well, you differentiate this exactly the same we are doing before, partial derivative. So this is derivative this and derivative this. Okay. Now you set up this integral. Look of this function, because we are another integral in which you replace x and y for the corresponding formulas for the parametrization. And ds, well, ds is the formula for the ln, que is absolute value, this guy, dt. Maybe in this moment sound weird. So even the student can remember the formula in Cal 2, never see in that way. However, I can modify it a little bit to understand much better. Wait, I don't finish. The limit is in between A and B, no? And you transform it like integral to the classical integral in Cal 1. Okay, repetition again. The limit is the same, A and B. The function you replace by parametrization formulas. And this is applied multiplication. This is not dot product, multiplication, regular multiplication. This is the magnitude of this vector, que is derivative is, with respect to time, s squared plus derivative is the y s squared dt. Maybe in this moment you don't remember very well because the majority of the teacher explain Cal 2 write the formula in another way. When I explain Cal 2, I explain in this way. Look, instead of this, you put dx dt using the linear notation, no? Square plus dy dt square dt. Do you remember now or no? Do you see that formula before or no? Answer me. In the chat. Activate the microphone because I don't see the chat. Yes or no?
That's what I was saying, Professor.
Total what?
That's what I was starting to say before you cut me off.
Okay, Untitled Chapter. Bam. So you never see that, right? No worries. You don't see one. Okay. Okay, now this is applied in 3 dimensions. Of course, we apply in 3 dimensions. Suppose you have now this integral. The integral function is 3D. In this case, we are talking about in this space x, y, c. So it's a curve C, but this curve C living in 3-dimensional space. It's 1-dimensional object. This is P1. This is P2. Exactly the same. P1 is x1, y1, c1. And P2 is x2, y2, z2. Cool. So the formula is the same. The formula is, look, you integration, you replace x, y, and z by the corresponding parametric equation. In this case, we have 3 parametric equations. It's obvious, right? It's x of t, comma, y of t, comma, c of t. So we convert my problem in 3-dimensional and 1-dimensional integral, que the parameter t. And the formula is square root dx dt a squared plus dy dt a squared plus tz dt. Square everything inside the square root, and don't forget, of course, the differential of the integral dt, and t vary between a and b. A and B are just a number, no point. So this is the point, but you have associated with this 1t equal A and 1t equal B. Make sense? Makes sense. It's important the orientation also, no? Who is the starting point? What is the end point? Okay. So we started today a new integral. This new integral is called a line integral. This is the name. And the only possibility to compute that is using parameterization. Let's see a couple of examples. One example in 2D and one example in 3D. Super easy, super easy. This is no big deal, guys. Look, example 1. Let me try to make zoom. Example 1. Example 1 say. Okay, let's compute this integral in the curve C of the YDS. So the integral function is just y. I did that to simplify the thing. Entonces, what extra information I need? Well, I need who is C. C is, we are doing, is given the graph, or is given the equation, no? Or both. XY is a quarter of circle like that, and the radius is 2. So at that point is 2, 0, and this point is 0, 2. And the orientation is extremely important in this direction. Orientation. Remember, parameterization needs. Can you define the equation? Need. Can you define the domain? And default, when you define this, automatically the orientation is defined also, no? Okay, so now we are familiar with the parameterization. Parameterization, remember, is not unique. This is important, complicated thing that the students don't understand very well. There are no infinity, but there are several ways to parameterization. Depending the curve, the nature of the curve, there are a best way to parameterization. What is the best way? The best way is when you are doing the parameterization, you will be able, okay, our parameter is in one line, not in 2 dimensions. This is T, and between A and B, this is the best way, because we ending my problem in one elementary integral like a Cal 1, right? However, if you are doing another way, maybe it's no 1 dimension, it's 2 dimension, it's another curve. This is wrong. Not wrong, but this is another parameterization, not best, not optimal. Okay, so I want to explain both ways. But in this case, no, you are familiar. When you are talking about circle, semicircle, quarter circle, the classical optimum best parameterization is cosine and sine, ¿no? Entonces, suppose que x es 2, que es el radio, cosine t, no new. Y is 2 sine t. And t vary from 0 to pi over 2, ¿no? Because it's a quarter circle. Entonces, basically, when you finish the integral after the parameterization, the domain is one segment que go from 0 to pi over 2. Okay? Now ready. Entonces, who is y? Well, y is easy. Y is, so you write again this original problem to another problem. Okay, I know that we finish in one elementary single integral from 0 to pi over 2, que es t, and everything inside here is a function of t. Who is y? Y is 2 sine t. And who is ds? Ds is a little bit more complicated. It's a square root. So I need to compute derivative, no? Derivative. Derivative of this, it's a dx dt, is derivative cosine and minus sine. This is minus 2 sine t. And derivative sine and cosine. 2 positive, no? 2 cosine. Then you write inside, according to the formula, no? Minus 2 sine t squared plus 2 cosine t squared, and don't forget dt. Okay, now I want to erase that part. Now you focus it, and that part is super easy. It's a 4 sine squared t, and it's a 4 cosine squared t, no? The part inside the radical. And you factor out 4, and you have sine squared t plus cosine squared t, get 1, you know, the famous identity, trigonometry identity, and the square root 4 is 2. Actually, my integral now is integral from 0 to pi over 2. You have 2 sine t, and you have extra 2, no? Que come from when you compute the square root of 4 get 2. Y 2 times 2 is 4. dt. And this integral is piece of cake. This is cosine minus cosine. Evaluating between 0 and pi over 2. This minus I put outside again. Yeah, evaluate cosine pi over 2 minus cosine 0. Sorry, I forgot the 4. Multiply everything. 4. Entonces, cosine pi over 2 is 0, cosine 0 is 1, but we have a negative, and double negative becomes positive. The answer is 4. Clear or es easy or no? Answer me. I need answer. This is a lecture, guy. Teacher and student. Without student, it's just a video.
I mean, I'm still copying it down.
So
my response is a little delayed.
Entonces, now, okay. See, I try to condense the information in a few words. You have the line integral, que es a new integral, but we can, using parametrization, you can convert to the one single integral exactly like L1. Because actually the parametrization allows us convert the problem in 2D or in 3D, let's say in the example 2, 3D, to the one dimension. One dimension que es T dimension. I can erase or no? I can erase or no? Yes or no? Answer me, please.
I mean, I'm finished copying. I can't speak for everyone else.
Let me know.
I'm done copying.
Excellent. Beautiful. I erase 1, 2, 3. Okay, let's move on to example 2. Okay, it's exactly the same, but the only thing I include new is that I put the problem in 3 dimensions. And that's it, but it's the same thing. Suppose compute this integral. This is y sine z ds. Do you understand the new idea who is ds? And who is c? Well, c is, this is the integrand function. This is our integrand function. This is f x comma y comma c. But in this case, x is missing. Okay, no problem. I understand. And ds depending of c. And c is the helix, circular helix. La que parametrization is x is equal cosine t, y is equal sine t, and c is equal to. And so you define t interval in between 0 to pi. This is given, not always is given. Okay, this is Healy, guy. Healy is, I suppose you remember, at least one time in our life, we see one Healy, no? Suppose t equals 0. Suppose t equals 0. Cosine 0 is 1. Sine 0 is 1 and 0. Entonces the point, that point, 1, 0, 0. This is at t equals 0. At t equal pi over 2, cosine pi over 2 is 0. Sine pi over 2 is 1. And t is pi over 2. So I include this at t equal pi. Entonces the answer, the point is 0, 1, pi over 2. And you plot that point, que es 0x, 1y, and pi over 2c, approximately pi over 2 is 1.57 something. There's one here, but 1.57. Entonces this, the helix look like something like that. It's a curve. I don't want to evaluate, pero es, you rotate several times. This is at t equal pi over 2, no? Que es the point, bueno, that point, 0, 1, pi over 2. And it's continue, no? Continue and stop in one moment. I don't know exactly, que es, I suppose que here, en pi over 2, en 2 pi, sorry, es the last, no? This is super easy to see manually here. It is crazy. In GeoGebra, remember the function curve. Entonces now you copy cosine t, comma sine t, comma t, because the parameter is the name of parameter, and 0 and pi and 2 pi. And you see elegant helix in GeoGebra. You remember that or no? Yes or no? Yes or no? Answer me.
Remember it vaguely.
Okay. Okay, so now to set out this is easy because this integral is equal another integral from 0 to pi is the limit of t because you change the domain, no? The domain of this is 3D. The domain of this is 1D. 3D, 1D. Y is sine t. Multiplication by sine z, and z is sine of t again. Repetition, sine. And sine t together is sine square, no? And ds, remember the formula, is a square root. And we have derivative, dx dt square plus dy dt square plus dz dt square. So basically, and don't forget dt outside. Easy. You differentiate the parametrization. Okay, dx dt is minus sine t. Dy dt is cosine, positive. And dz dt is 1, because the derivative with respect to t is 1. So you replace, no the formula anymore. No. You copy that now. This is minus sine square t plus cosine square t plus 1 square, no? Bueno, sine negative sine square es positive. And sine plus cosine es 1 y 1 plus 1 es 2. Entonces, basically, my integral is reduced 0 to pi. This is sine square t. And everything here is radical 2. If radical 2 is a constant, I put outside again. Okay, easy, 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 easy. This is the, see, you are doing by hand, we're using the half angle formula. The half angle formula is 1 minus cosine 2t over 2, no? Entonces you separate this integral, for example, into integral. You split this common denominator, no? Entonces 1/2 t dt. Okay, this is a common factor. And another is minus integral from 0 to pi cosine 2t dt. Okay, so you are doing this. I want to skip this. This guy is 0 because the cosine double angle and one period is always 0. However, this no. This is 1/2 and 2 pi. This is pi, no? Because integral 1/2 dt is 1/2 is a constant outside again, but it's t evaluating between 0 and 2 pi is actually 2 pi. So 2 pi divided by 2 is pi, and the answer is pi. Boom. Final answer. Do you understand very well or not? So it's no big deal. The magic of the line integral is parameterization. You parameterize, and you convert the line integral in 3D or in 2D, and one single integral exactly we are doing in Cal 4. So far it's clear? Okay, but I want to complicate more this. Because the line integral we studied so far is the line integral in the scalar function. This function is scalar. Entonces, bueno, the interpretation of this professor is a mass of the wire. So you consider that this is the linear density function. Okay, I understand this. However, I want to complicate because now we apply the line integral in the vector field. Okay, so we have line integral over vector field. Entonces we study in detail everything. Interpretation, the way to compute that, okay, there are many ways. The first, basically, there are two possibilities to apply the line integral over the vector field. The first possibility is circulation. Okay, I want to explain in detail the meaning of it. Another is flux. So we are talking about in this chapter, guys, circulation integral, flux integral. For a moment, forget about flux because it's a little bit complicated to explain now. But I want to explain today. We focus 100% in circulation. What is the formula of the circulation? The formula is you apply the line integral along the curve C is given, of course, of the vector field. Dot product now, no regular multiplication. And the other integral we are doing line integral, scalar function. Yes. What is the operation, the arithmetic operation in between this and this is multiplication. I don't indicate the period here, but it's multiplication. In this case, no multiplication. It's a dot product. So now. Wait, hey, it's a rule. Wow, the rule is working now. Cool. Okay, erase that part, I don't care. Surprise. And we have here dr. And what the hell is dr? And dr is a vector. Es obvio que es de vector, because es dot product in between two vectors, ¿no? Ajá. Entonces, now, dr es el vector, que es el vector igual tangent vector 10. Tangent vector 10. Ajá, bueno, okay, dr is also possible. There are many ways to express the formula for dr. dr is the vector dx, dy. En two dimension, ¿no? En three dimension es dx, dy, dz. But what's the meaning of that? So basically we have vector field. Suppose bang, bang, bang. Remember vector field is a bunch of vectors, no? And the formula always is given. We have the curve. Ajá, entonces I want to determine the circulation, the line integral circulation, and between the point P1 and the point P2. There's any point, suppose arbitrary. I have the vector field here, suppose. Y I have dr, que es a vector in this direction. Tangency. Because somehow, depending of the, so it's a vector que depende de tangent unit vector that indicate direction, and the S is the classical at length, infinitesimal. And you perform the dot product in between vector field, point by point, dr, point by point, que es different. So dr here is another dr, and apply the integration, que the integration is the Riemann zone of this. Okay, do you understand the idea for the line integral over the vector field and the way of circulation? I want to explain another way after, no circulation. Entonces, bueno, okay. I understand mathematically, but what means the physical meaning of this? No, physical meaning is all because word. Bueno, no, okay. Es word under the supposition that the vector field is a force. Suppose we have a vector field. Vector field is, in general, mathematical. Vector field is a vector, but this vector maybe is a force, or maybe is velocity, or maybe is linear momentum, or maybe is acceleration. O sea, in general, pero suppose hypothetically, to try to find a meaning of something, for the moment, I suppose that our vector field is given in my problem is a vector field of the force. So es en Newton. And when you compute the line integral and on the curve, you are computing the work done for this vector field when the one hypothetical particle travel from P1 to P2. It's a work done for the vector field. Clear a little bit, no? In general, not necessary word. Mathematically, is circulation line integral. Okay? I try to find always the connection with the physical interpretation or geometric interpretation. Cool? Okay, cool. Now, one more. So what is the formula, Professor? Well, there are different formulas. I want to compare in different formula now. But for example, one very popular formula is this. I suppose always we are doing now in two dimensions. Suppose that the vector field is PQ. Remember, PQ are a function, a scalar function, that depending of x and y in two dimensions. So this integral, dot product, dr, is equivalent to say integral in vector field is p, q, dot product, and dr is dx, dy. Along the curve C. Now, Now. You perform the dot product, que es multiplication this and this, and this and that. And you have this line integral p dx plus q dy. Wow, fantastic formula to compute the circulation line integral. But the only disadvantage of this formula is que no, bueno, we can use it in the parametrization, pero okay, it's important, guys, to understand. We have the parametrization using T, as always we are doing, but we have the no parametrization, okay, using X and Y. So we can use this formula in the majority of the problem que no necesarily. How do you know que you need to parametrize or no? Well, depending the curve. Si the curve is a circle, it's obvious que the best way to parametrization is cosine sine. Si the formula is no circle, it's a line or parabola, I don't know. Pues entonces now it's much better doing in the no parametrization, or I call in my language, the book called different. It's a natural parametrization. It's X, Y, no parametrization. Okay. So let me try to discuss it now before I start problems. Interpretation for the circulation. I bring for you one picture to help me a little bit to understand circulation. Do you see that? Do you see it? Do you see? Okay. Do you see or no? Answer me. Do you hear the rain?
Yeah, it's pretty strong.
Okay. In blue color, we have vector field. In red color, I guess so, we have different curve. I want to analyze the no exactly values, qualitative value of the line integral in this triangle. Suppose C1 is this curve, C1. So now when you travel in this direction, I suppose that you go in the same direction of the vector field. So there are perfect coincidence in between F, que es the vector field, in any point that's different, and dr. Okay. Dr is a vector que es tangency to the curve. In this direction, well, same direction. In this case, same direction. In this case, same direction. Therefore, I conclude que is the integral, when I finish the problem, give me a positive value. This idea is cool? This idea is okay?
Sorry, could you repeat that one more time, Professor? Sorry,
Okay.
the rain.
Okay, don't worry. This is me. I travel on the curve. This is me. I travel here. Bang, 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 bang. I analyze the orientation of the vector field. For example, the vector field is in this direction. Now it's in this direction. And dr is a hypothetical vector que es tangency to the curve. It's a dr always. And you see in this figure, I don't want to repeat again, que always happen, there's no coincidence, I did intentionally to illustrate this idea, que it's in the same direction, no? Entonces, the dot product is positive. And the summation for the infinitesimal dot product, the answer is positive. Cool or no?
Cool. Thank you, Professor.
No problem. Now, suppose the curve C2, que actually is no closed, it's like that. In this direction. So you see when you go up, it's the same value, no? It's the same value, so the same orientation. So the vector field, in my vector field is the arrow. Let me make a zoom. Que es in blue color. This is the vector field, and in green color I put the trajectory, no? the curve, and you go upward in the same direction, but you go downward in the opposite direction. You say cancel out each other. Yes or no? And the answer, I suppose, I don't know si es zero, but I infer si es symmetric, que the positive part and the negative part cancel out. Make sense? Make sense? Make sense or no? Yes or no? Answer me. In the curve C2, I predict que the line integral circulation is zero. Yes or no?
Yes.
Yes. Do you understand the idea, no? The idea is super straightforward, no complicated. It only si I travel in the same direction, entonces suppose que it's a word, the word positive. Si I travel in the opposite direction, the word is negative. And C3 having similar idea. Look at that. I travel along the curve. In this case, opposite, in this case, in the same direction. Cancel out each other, it's zero again. Yes or no? And C4, what is C4? C4 is this line. No turn in. So it's in this, it's completely in the opposite direction to the vector field, no? That is a reason that's negative. Do you see or no?
Yeah, we see.
And C5 is zero because in C5, let me try to understand. And this in C5, who is C5? C5 is this line gets completely perpendicular to the vector field in this region. Therefore, it's zero. When you perform the dot product, it's all because. And finally, the curve 6 is the closest in this direction. It's the curve C6. You travel in this direction. When you travel in this direction, for example, in that part, you see the direction of dr is a little bit opposite to the vector field. In this case, it's opposite also. In this case, is opposite. And in this case, is opposite. Opposite. It's negative. Do you see that? Always is opposite. Okay, guys. This is direction vector field. This is my curve. When you travel, my dr is this vector. No? Same direction. The dot product. It's obviously positive. Suppose another example in which the vector field is opposite. Same line, same direction. dr is this. This is dr. The dot product is negative. Makes sense, right? Si es 90 degree. Si es 90 degree. Suppose one more time, this is my curve, this is my dr, this is the direction I move. However, the vector field is in this direction. Es 90 degree. Entonces now dot product es zero. This is clear, eh? Super clear. Do you understand very well circulation? Line integral circulation is line integral on the vector field. So participate always, the integrand function is no scalar, no, it's a vector field. The vector field is given. The vector field is given, and the curve is given. Yeah, I need to find the line integral circulation. Clear or no? Let's see example. Professor, I understand the concept. Now example. Let me bring example elementary, and I complicate little by little this. Example 1. Line integral circulation. Imply vector field. The vector field is given. It's the famous x comma y that we studied last class. I want to recall this guy. And I need to compute the line integral circulation of this vector field, no product dr, and C. Who is C? C is a circle. It's a unit circle. C is the unit circle. Unit circle. Unit circle. I don't do very well, but it's a unit circle. It's a 1, it's a negative 1, it's a 1, it's a negative 1. And this is a problem in 2 dimensions. Okay. Now, the best way to parametrization is using the famous cosine sign. And the orientation, guys, is in the classical orientation. No complicate this. Counterclockwise. Entonces es obvio que es cosine t, because the radius 1, no? And sine t. And t vary. Don't forget to specification. This is important because you no conclude the domain. So I don't know si it's a full circle or it's a quarter circle, semicircle. It's important this. So now, I perform dot product and between the curve C. Who is F? F is x comma y. Entonces cosine t comma sine t. Dot product, and dr is dx dy, no? Entonces to find dx dy, I need to find the derivative, no? So the derivative dx dt, derivative cosine is minus sine. But I don't want dx dt, I want dx. Well, dx is equal minus sine t dt. You multiply this. Likewise, dy dt is cosine t. Therefore, dy alone is cosine t dt. Okay, ready. My line integral circulation is integral. So now it's a moment that I don't put C anymore. I put the limit is 0 to pi because I know everything is expressed like a function of t. And so you convert the problem of the line integral circulation in a single. Well, actually no, because look, it still have the problem. No? Okay. So much better. More strictly. Line integral so far. So this is cosine t, comma sine t, dot product, and dx is minus sine t dt, comma cosine t dt. Now you perform the dot product. This time this time that. So we have integral now is from 0 to pi. So we have multiplication cosine t minus sine is minus cosine t sine t dt plus multiplication is sine t cosine t dt. Es obvio que es 0. Es obvio que this es cancel out. You factor out dt. Es 0. Entonces the answer es 0. Oh, entonces what's the meaning physically? The circulation is 0. Well, first of all, the vector field, let me try to do my best. You remember last class, this vector field look like that, completely radial. In the last class, do you remember, right? You remember the source, because divergence is 2. Entonces, now, if you perform mentally, physically, not mathematically, the dot product between the vector field, que is always in this direction, and the r vector, que is always in this direction. Oh, no good. In this direction. So it's tangential to the. You see que es orthogonal. Orthogonal. Therefore, si es orthogonal, the angle is 90 degrees. Therefore, the dot product is 0. In any point. In any point is 0. Do you see that or no? And you prove mathematically. Easy or no? At least this example. Another no. Another is a little bit more complicated. Let's move on to another example. To see another approach to compute the circulation. Suppose example 2. Suppose the vector field is given is x squared, comma, y. And I need to compute the circulation, the integral. Dot product. And the curve que is given in this problem is it's a parabola. It's a parabola like that. And the equation for this parabola is x squared minus 1. That is the reason that we have y instead 1 here. This is a negative 1. This is a 0.0, negative 1. But I want to compute the circulation line integral in one specific. I need to specification 2 points. This is the first point, P1, que is negative 1,0, to this point, P2, que is positive 1,0. And using this orientation in this direction. So you are doing in opposite direction, it's the same value, but opposite sign. Suppose that when I finish this, the answer is positive. I don't know. So you change the orientation, for sure, I guarantee you, okay, the answer is negative. But in this example, I bring this example intentionally because in this example, it's not good, the parameterization cosine sine. This is only possible in the circle, semicircle, quarter circle. But in this case, it's much better, most convenient using the natural parameterization. This is my way to call this. It's actually no parameterization. It's x is x, y is y. Okay? Entonces now, I'm using no this formula, sino this formula. Integral p dx plus q dy. Remember, I explained where come from this formula. No? This is my p, and this is my q. And the vector field. And the formulas, the parabola is, okay, I want to travel on the parabola is x squared minus 1. Okay. So I need everything. I need x, I need y, dx, and dy. It's easy. And the natural parameterization, x is x. Okay. And y no. Y is this. And what about the x? The x is easy. The x is the x. Because derivative of the x with respect to the x is 1. And dy is 2x dx. Make sense? You differentiate these with respect to x, is 2x, the constant is 0, is x. Ready to plug in everything inside the formula. Natural parametrization is my name. You never see in the book this terminology that I use in my lecture for the student to understand. I suppose to understand. You let me know. Okay, so now you are doing the transformation, this circulation line integral in this vector field for the one classical regular integral, the cal1, can go from -1 to +1. Because, by the way, I forgot to say that x vary from -1 to +1. This is the, like a t, pero no es t, es x. So you replace, who is p? No, p is x squared. Who is dx? Well, dx is dx. No difference. Plus, who's q? Well, q is y. But who is y? Y is x squared minus 1. So I don't write like this because my intention is convert to the one integral like a cal1 that contains only one variable. It doesn't matter if you select y or x. I prefer x. So actually, no y anymore. No. Y is q. But I write on this line the relationship between y and x is x squared minus 1. Multiplication by dy, and who is dy? Dy is 2x. Cool? Do you understand this? Well, the rest is multiplication. Apply the thing you know about the integral in one variable. Separate in two, I don't know, find the antiderivative, evaluate between -1 and 1, and the answer is 2/3. Do you understand very well this or no? Cool or no? Opinion?
So professor, in this problem, does the 2 dx, does it matter that there's 2, or do you just combine both equations?
No, of course you combine. Either way, you combine or you separate. Either way, using your common sense and imagination, you separate this, and you multiply. This is 2x QB minus 2x dx.
Okay.
Either way, or you put together. Cal1.
All right. Just wanted to, thank you.
Oh, it's okay. Let's move on to the little bit more complicated stuff. Not too much, but a little bit more. Suppose we continue doing line integral over the vector field circulation. Example 3. Vector field is always given, no? It's requirement. X times y, comma, x minus 1. And you need to compute this vector field dot dr and the curve C. And the curve C is a little bit complicated curve. Not too much, but it's a little bit. Can contain two pieces. The first piece is from the origin 0,0, travel in this direction to the one specific point is 2,0. Guide, the orientation is mandatory. And travel, stop here and travel to another point is the point 3,33333. This is 2, this is 3, 3,2, 1, 2 here. another point here. Okay. So my curve C actually is C1 plus C2, or not exactly plus, it's C1 union C2. Es ese compound curve is formed by two pieces. There is no secret sometimes happen. Yeah, I need to compute the okay, by the way, this point is the point 3,2, no? Okay. So what should I do? We apply the same formula. I prefer using this formula. PDX, QDY. I using this formula because it's a line, a segment of line. See a circle, semicircle, so you are doing the classical parameterization. Cosine, sine. And this is the natural parameterization, XY. So now I analyze, but analyze segment by segment. So I compute the first and the curve C1 alone, only C1. It's integral C1 PDX QDY. And the curve C1 happen the same situation. X is X, no problem. It's independent variable, free. But why not? Why is 0? Because we travel along the x-axis. Therefore, differential x is equal to differential x, but differential y is 0. Wow. Okay, so say I go to the formula, integral C1 with P. This is P. This is Q. But you evaluate in this condition, que is the condition along the C1. C1 is 0, it's obvious. Okay, the vector field, so the P is 0. So the vector field, let me copy here the vector field. Vector field formula only in C1. Let me call F1. Is CY is 0, 0 times X is 0, comma, X minus 0 is X. This is the formula for the vector field. This is my new P, P1, Q1, specific on the C1. Okay, entonces 0 dx, no problema en esta, plus Q, que Q es X, multiplication by dy, que es also 0. This integral es 0. The reason que es 0 is because I suppose que es orthogonal. So the direction for the dr and the vector field, but you don't see clear. But we can use him if you want after one application to see this, at least this example and the circulation. I send to you two script in GeoGebra to analyze this idea. I want to show you when you finish this example, at least this example. Okay, I finish. No, I need to analyze C2. C2 is the second part of the curve in which, of course, X is X. This is classical natural parameterization or no parameterization. Why not? Y is the equation for this line. Okay, I don't want to explain how you compute that because everyone knows very well this. You find the slope, find the point slope formula, and you determine that the y is 2x minus 4. Now, the differential dx is dx, but dy no. dy is 2dx because you differentiate this with respect to the x is 2, the derivative 4 is 0, and f2 vector is well, you try to convert my problem in only one dimension. To say integral C2 vector field F dr, the product is integral C2 P dx plus Q dy is integral. Who's P? Well, I don't know. P is you replace y, this y here, a multiplication by x. It's easy. It's 2x squared minus 4x. Makes sense, right? Multiplied by x. This x is outside. Comma, and you likewise, you replace this x minus 2x, well, minus 2x plus 4. Entonces, combine like term, is x minus 2x is minus x plus 4. Make sense? Make sense? Okay, look, x minus y. But who is y? Y is 2x minus 4. X minus 2x plus 4. Combine like term, minus x plus 4. And this is Q2. P2. And use substitution. Entonces, P2 is 2x squared minus 4x. And dx in the formula is dx. They have no difference. Plus q. Q is minus x plus 4. And dy is 2dx. And this varies from 2 to 3, no? Is the value of the x in the curve number 2. Guys, this is elementary. Separate into integral or no. Your multiplication, put together, antiderivative, evaluate between 2 and 3. The answer is 17 over 3. Okay, by the way, is approximately in decimal 5.6. Repeat it. Yeah, because 15 to third, no? 15 to third. So you divide 17 divided by 3 is 5. 15 to is 5 to third. A mixed number. What is the reason? Because now in the application that I put here, you see the numerical value, no? Entonces in the GeoGebra, you see the numerical value in decimal. Okay, let me show you. This is the last part. I will continue next time. It's the most complicated part. Okay, let me try. Okay, I open. No chat anymore. Okay. Let me try to do my best. Boom. Circulation. When you have time, today or tomorrow, you open this application. Look. Let me share the screen. Switching to the algebra. So I sent to link. Okay, you can working online with this application. Do you see the application or not yet? Do you see or not? Do you see? Do you see or not? Answer me. Guy, remember, I don't see the chat. So now I activate the microphone to say yes, no. Okay, this yes, application. Yes, okay. This application, fantastic. Look, for example, you put the vector field, you see in the application F1, F2. This is PQ. Different language, same idea. And you have the vector field. Oh, it's weird. Look at that. You see, or you put a hide. Now you see different style of the curve. Segment line, right circle, left circle, or full circle. In this case, we are working with this segment line. And remember, our curve is formed by two segments. The first one is the segment can go from 0 to 2. You see the point. This A represents the starting point, B represents the ending point. And this is the answer for the circulation line integral, 0. And by the way, Bueno, okay, so you want to see the tangent vector in red color. In this case, is collinear, no? To the segment, it's open. Now, suppose so you want to see or know the vector field in the second piece of the curve from 2 to, okay, to 2 to 2, the point A is in 2,0, and the point B is the start point 3,2, 3,2, 3,2 is here. There you go. And you see the answer is 5.67, exactly we predict in the calculation. Okay, it's 2/3, no? Makes sense? Beautiful? Beautiful? And the tangent vector, you can see tangent vector. In this case, though it's not clear tangent vector because it's coincident with the 7. But suppose I want to change a circle, suppose. Do you see the tangent vector? No tangent vector, tangent vector. And you understand a little bit the sign of the circulation. In this case, look, suppose circle in the origin, 0, 0. This is 3.14, I suppose it's pi. We compute another example que es the radial vector field. I suppose you remember que es x and y, no? Let me change. I can change. I can experiment with this. In my opinion, this is amazing, guys. Look, you click here. You see the vector field is radial? And the tangency, the tangent vector is the red color, and the circulation integral is 0. The 0, we prove in the example 1. 0. Independent of the radio, look. Different radio is the same. Do you see or no?
Yeah,
Do you see or no?
Yeah, we see.
Okay, we continue now. Next time, Monday. This is a complicated part, guys. Okay, listen to me. One more thing. We study, let me try to organize your brain. Line integral. Line integral is possible apply in the scalar function. Okay, what meaning? Mass, maybe. We apply over the vector field in two different possibilities. Circulation. So not necessarily circulation is around. Circulation is moving. But the important is que es tangencia. But we have studied another next class is flux. This is the most complicated part that the student never understand very well. Flux. Flux is, you suppose, que it's a fluid, water, or whatever, or gas, and you have surface. I need to find how many vector field passing through the surface. Flux. It's another kind of the line integral. And we study in 2 dimensions now. And after we study in 3 dimensions. But no next class. Next class is in 2 dimensions. Next is in 3 dimensions. Okay? Okay, bye guys. Entonces now you start working in the lab online. It's complicated in this part. Very, very, very complicated. Everything is complicated. I told you.
Have a nice day.
You too.